Can people hear me?
Yes.
All right, very good.
Okay, so we're ready to start the second session of the morning. So we're very happy to have Michel Janssen from University of Minnesota and University of Bonn.
Mhm.
Okay. And he will be telling us about Einstein gaining a foothold in the quantum world, 1904 to 1925.
Okay, thank you. Thank you very much. I'm very pleased to be here, even though the talks are kind of over my head. I'm very honored to be invited. It's also the closest I'll ever get to giving a TED Talk. So I've seen TED give talks, and I've always enjoyed these. Last time was like last year in Slovenia. Little mistake there in your slide. It was in May, not in June. But the talk where I first saw TED and which inspired this talk was one he gave at New Directions about 20 years ago. And so I was there with one of my mentors, one of my intellectual grandfathers, really, John Stachel, who passed away at age 97 last year. And I was sitting next to John and one of his associates as Ted was giving this talk. And after the talk, I turned to John and I said, like, that's the first talk about, the first ever talk I've heard about quantum gravity that I thought was good. And so John turns to me and says, like, but I've given talks about quantum gravity. No, I'm sorry. So his associate says, like, yeah, me too, the first good. But I've given talks about quantum gravity. And so the associate says, like, oh, I forgot. And I said, but I didn't. But I was John's grandchild, and grandchildren, of course, can do no wrong. So, so John forgave me. But ever since, I felt I needed to explain, like, why I thought this was a good talk. And so most of that was over my head. But just if you look at the abstract, I just like the structure of this, right? So there's, okay, like we have these two assumptions here, then we get this, and how do you argue for these assumptions? Well, there's deeper results that you can like appeal to do this. So rather than just speculating into the blue, the strategy seemed to be like, what can we learn from stuff that we actually know? And I think that is very much like what Einstein did, like when he was working on quantum mechanics, right? And so, or quantum theory early on. So that's what I want to show you. And so I'm going to start with like a distinction that Einstein made. There's a lot of ink has been spilled about this. He made this in an article in the London Times in 1919 between constructive and principal theories. So in a constructive theory, you speculate, you have like a certain model, and then you show that the phenomenon are in accordance with the model. And the example that Einstein gave is the kinetic theory of gases. The other one is a principal theory where you start with well-confirmed empirical regularities. And the example that Einstein gives is like thermodynamics. Now, again, a lot of ink has been spilled. My claim is, I'm not going to argue for this, I'm just going to, posit this, that Einstein made this distinction not to put labels on like finished theories, but to distinguish between different strategies for finding new ones. And so the maxim is, like, if you have no idea what a satisfactory theory looks like, that would be a constructive theory, find constraints of the model. That is, like, develop a principal theory. And the question then becomes, like, how did Einstein find such constraints? So one strategy that I've written a lot about is to exploit unexplained coincidences in existing theories. And so that you see in relativity, you see the famous magnet conductor experiment, like in the first paragraph of the 1905 paper. The question is, like, why is inertial mass equal to gravitational mass? And in a way, that sort of got the whole thing about general relativity started. Now, enough about relativity. I think like the strategy is much clearer in the case of quantum theory. And it's sort of, like you can sort of understand why. So in the 20s and 30s, Einstein thought that he knew what a satisfactory model of the world looked like. It's something like general relativity. Like, so he worked on some classical unified field theory. But in the 1910s and 1920s, Einstein was very aware of the fact that he had no idea what a satisfactory model of the quantum world looked like, right? So he followed this principal strategy. And there's a famous anecdote. Unfortunately, this is now like almost certainly apocryphal. Einstein is working in Prague. His office is overlooking the garden of an insane asylum. There's people like walking around. His successor, later biographer Philip Frank, comes to his office, and Einstein says, see those people over there? Those are the madmen who do not think about quantum mechanics. So that's the thing, right? How did Einstein, gain a foothold in this quantum world? And so I'll be talking about all the stuff I say comes from these two books that I worked on with Tony Duncan, physicist in Pittsburgh. And there's another very nice book by Doug Stone from Yale University, written for a general audience, which I can highly recommend, Einstein and the Quantum. And you can also now look at the original papers, in a very handy edition, edited by Diana Buchwald and Tilman Sauer. And so what are the contributions? It starts with the statistical trilogy. Then in 1905, you had the light quantum paper. You have, in 1906, you have the quantization of the oscillators in Planck's theory. You have the use of those oscillators to develop a quantum theory with specific heats. In 1909, this is my favorite example, a lecture in Salzburg, where he gave a fluctuation argument for wave-particle duality. In 1905, he's given a fluctuation argument for just the particle nature of light. 1617, after working on GR, he comes up with the famous A and B coefficients paper. And again, another derivation of the Planck law using fluctuations. And then, skipping over a bunch of things, the final contribution, inspired by Bose and de Broglie, this quantum theory of the ideal gas, where he repeats this fluctuation argument, but now in the context of matter rather than radiation. So I want to go through the whole thing, okay? So there's no time to do this in detail. I'll show you a lot of the details, but these are calculations that you're all very familiar with, so I think I can move fast. But like Ted, I'm very interested in teaching, so part of the reason I'm showing you this is to convince you that, if I slow down a little bit, I can explain this to physics juniors and seniors. Okay, the statistical trilogy, right? So Einstein is laying the foundation of statistical mechanics. He is blissfully unaware of the work of Gibbs, doesn't know most of the work of Boltzmann. But here he develops the idea of using fluctuations to probe the microstructure of macroscopic systems. He derives the fluctuation formula for the canonical ensemble. And then, in the final installment, he does something very interesting, he applies this now to black body radiation, right? People before them applied to gases. And so he's going to give a rough estimate of energy fluctuations in black body radiation in a cavity that has the dimension of the maximal wavelength, right, where the peak of the black body spectrum is. And he's going to assume that the mean square fluctuation is of the order of magnitude of the mean energy. And so he uses the Stefan-Boltzmann law, and then inserts that into this fluctuation formula, and that gives you this here. And so Einstein actually gets this wrong because he forgets that lambda max to t is a constant, right? So he gets an extra factor of 4 here. So if you then use this ansatz, you set these two things equal to one another, and that then gives you an expression for this, right? It's just the ratio of these two constants, Boltzmann's constant and the Stefan-Boltzmann constant, and you can put those in. You get this value. Einstein gets a slightly bigger value because of this mistake here, and then you can get this from black body radiation, and you find that this is very, very close. If Einstein had not made the mistake, it would have been even closer. So what he concludes is this inspires confidence that indeed this application, which is controversial, makes sense. Okay, we can apply the canonical ensemble to deal with black body radiation.
Did he give any arguments to justify the second line?
No, he did not. So but Tony tells me this is a reasonable assumption to make, but I'm kind of puzzled by this. All right. So now that confidence will not last. Okay? So then in 1905, we get the miracle year, and the one paper, of course, that Einstein himself calls very revolutionary is the light quantum paper. And so the opening gambit is to show that classical theory, or classical I put in scare quotes, because like, does this or does this not include something like the equipartition theorem, leads to the Rayleigh-Jeans law, right? And so Planck has put a lot of work into deriving this relation between the energy density of black body radiation and the mean energy of a resonator that's interacting with this radiation, okay? And so Einstein uses that relation and then just applies equipartition, not to the fields, but to the resonator, right? And then like sees that, okay, that leads to the Rayleigh-Jeans law. That's a disaster. How do you get out of this? Okay. Well, one thing is to deny equipartition, right? There's the famous line by Rayleigh, what would appear to be wanted is some escape from the destructive simplicity of the general conclusion relating to the partition of kinetic energy. Another one, and Doug Stone does a real number on this, is to deny equilibrium, right? That you just the black body never reaches equilibrium, so he calls this calamity genes with a slow catastrophe theory. And the problem is that a lot of these results in like the Stefan Boltzmann law, are based on the assumption that you have equilibrium, and you have to assume that those are then lucky accidents. In fact, the great Lorentz recognizes that, but says like, all right, even though I'm going to go with this, even though it obliges us to attribute to chance the presently inexplicable agreement between observation and the laws of Boltzmann and B. Now, of course, there's the other objection that is pointed out to Lorentz. Lorentz realizes that himself, that if that law were correct, then like a metal plate at room temperature should glow in the dark. So Einstein accepts both equilibrium. He's suspicious of coincidences. We saw that with relativity. And he also assumes equipartition, at least for these oscillators. And instead denies the wave theory of light, or the general validity, right? And comes up with the light quantum hypothesis, stated very carefully in the beginning: propagation of a light ray. Energy is not distributed continuously, but consists of a finite number of energy quantities, localized at points, move without dividing, and can be absorbed or generated only as complete units. And he's going to give like a fluctuation argument that I'm sure you've all have seen in support of this like quantum hypothesis. He derives a formula for the small probability of a large fluctuation in high frequency black body radiation, and shows that formula has the same form as a formula for the corresponding fluctuation in an ideal gas. And then concludes that, they behave the same. What inspired that argument, I think a clue is given in the opening sentence of this famous A and B coefficient paper, where Einstein says the formal similarity between the chromatic distribution curve for thermal radiation and the Maxwell velocity distribution is too striking to have remained hidden for long. Again, using this idea that you should be suspicious of coincidences. All right. And so now, to calculate this probability, he's going to use what he calls Boltzmann's principle. So no longer relying on the canonical ensemble, but just writing S equals K log W, right? So here is the, you can't really see it on this picture, but here it says like S equals K log W, written down in that form, not by Boltzmann, but by Planck, and turning it around and say like, that basically the probability of the number of microstates is E to the S over K, entropy over K. And my guess is that he realized that since the particle number in general won't be conserved, that you cannot use the canonical ensemble. It's a guess. All right. And what he now does is he goes through Planck derivation of the Wien law, which Planck did before he found the Planck law in 1899, in reverse. So what Planck used was like a formula for the entropy of a resonator, and to find like a formula for the energy density, right? And then, using this relation between rho and U, first he finds the energy density for the resonators, the U, and then he has this relation between U and rho, he gets that. Einstein starts from that formula, rho, that he gets, and then works back to the entropy, or the entropy density. Okay, so here's how it goes. So this is the Wien law. So you solve for T. From thermodynamics, right, you have now that, the SDE is 1 over T. In terms of the density, it looks like this. You integrate this, you get the entropy density. You move from the densities to the entropy and the energy themselves, you get this. Now you look at the change in entropy if you go from a volume V naught, big volume, to a small volume V, and you get this expression. And so he says, okay, the probability of like a spontaneous fluctuation, right, where you have like the black body radiation in the Wien regime in this big volume going to the small volume is given by this expression. Okay? And so he says, okay, like you can do that for like an ideal gas as well. And the probability in that case is just the ratio of these volumes to the power of the number of particles you have. And that suggests that in the case of black body radiation in the Wien regime, it behaves like, n particles with like energy h nu, right? So he concludes monogrammatic radiation, like he's focusing on one frequency of low density in the range of validity of the Wien formula, behaves thermodynamically as if it consisted of n mutually independent energy quanta of magnitude h nu. Now, if you paid close attention, so Einstein actually skips over a few things. Okay, so there are some complications with this argument, and again, I'm interested in sort of Einstein's general MO, and so here's an interesting comment he makes in his obituary for his close friend Ehrenfest, where he says, like, Ehrenfest suffered incessantly from the fact that his critical faculties transcended his constructive capacities. In a manner of speaking, his critical sense robbed him of his love for the offspring of his own mind, even before they were born, right? So Einstein's attitude is very much, you should give these ideas a chance. Okay? Like you see, I've seen this like when he's working on general relativity as well. Like, ignore problems, if you don't know what to do with them and hope that somehow they will resolve themselves. And sometimes this works. I want to shout out here this beautiful new biography of Ehrenfest and his wife by Margriet van der Heijden. Just came out in English translation. Denken is verrukkelijk is the Dutch title, like thinking is delicious. But there's a bunch of complications, and like I'm sure you've spotted a few already. Right? So first of all, Einstein is using like a formula that holds for equilibrium for the entropy to deal, to calculate the probability of a fluctuation way out of equilibrium. So I think that, that's not that much of a problem because, like, so the system is going from this one state to another state, and most of those microstates will also be like an equilibrium state, like for this new situation. Okay, right? Again, I'm moving fast. Another one is that Einstein actually explicitly calculates the average energy of light quanta in the Wien regime, right? So this is the calculation. So you calculate the energy of the black body radiation and divide by the number of light quanta. So the numerator, right, you just like calculate this. For the number of light quanta, right, you calculate this and then divide by the energy in one light quantum. Get these integrals. These are standard integrals. You put this in, and you get 3 kT. Now, if you really want to insist that these particles behave like ideal gas molecules, that's twice the value you want. Like for gas molecules, it's like it's 3/2. Okay, so like say, okay, but there's 2 modes. Well, it doesn't quite work. So what is the response here? Analogy is not perfect. Number 3, this will become important later on. The entropy is not additive. Okay, so this is roughly the formula. If you introduce the number density, you can rewrite this like that and like this, right? So now you get this term with the log of n factorial. And so now, so this is what you get. Imagine that we have a cavity with black body radiation. We're going to insert like a partition. So we have like VA, NA, VB, MB. The density, number density is the same. And so we calculate the entropy on one side, the entropy on the other side. We add the two together. But if we calculate the entropy of the two combined, right, you get a different result. So this is not additive. There's a simple way to fix this, and that is to add like a factor of n factorial to the definition, right, with some hand-waving argument that these particles are indistinguishable. And so now, of course, like you subtract that troublesome term, And if you now do the same thing, you see that the new entropy behaves just as it should. It is additive. This will become important later on. The fourth complication, so the problem with this fix is that, like this whole notion of indistinguishability, of course, is still like 20 years off. And this factor n factorial creates other problems. Complication number 4, and this is something that Tony, as far as I know, first put his finger on. And that is that this fluctuation argument supports only part of the hypothesis. And probably I went too fast, but like there's an interesting discrepancy between the conclusion of the fluctuation argument and the statement of the hypothesis at the very beginning. Because what's missing from the conclusion is this bit that they're localized in space. Right? So basically the hypothesis has these 3 components: discrete, independent, and localized. And the argument only supports 1 and 2, but not 3. So maybe Einstein left this out on purpose. I think it was more of an oversight, but this is like speculation on my part. So the fluctuation argument also works for quantized, non-localized waves. And so this is something that Ted has been pressing me on. Like, people must have understood that you could do that. And sure enough, like some of them did. So the total energy, right, comes in n quanta of h nu, but there's 2 possible ways to read this, like as n localized point particles with energy h nu each, or as n modes of standing waves in some narrow frequency intervals in the Wien regime with energy h nu each. Okay? And the fluctuation argument works in both cases. So I'll give you like a quick rundown of how this works, right? So the W is just in S equals k log W. It's just the number of ways in which you can distribute these n quanta over the available modes in that interval. The number of available modes is proportional to the volume V of the cavity. In the Wien regime, the number of available modes is much greater than that number n. And hence, any available mode has at most 1 quantum of energy h nu, which means that the ratio of values of W before and after fluctuation is precisely that same ratio of the two volumes. Hence, like these quantized waves also behave like ideal gas molecules. And nobody pointed that out at the time. Even though, like de Baeye in 1911 is using quantized waves, nobody says, oh, but these things are non-localized. This bit is wrong. Here we are. So what is the importance of this argument for Einstein, right? And so my colleagues, Rob Raniszewicz and Jürgen Wenn, they've dubbed this Einstein's fixed point strategy. And what you have here is that there's 2 seemingly very secure results: Boltzmann's principle and the Wien law for black body radiation at high frequencies, right, where the Planck law will just reduce to the Wien law, imply some particle-like behavior of black body radiation in the Wien regime. And that gives you then a constraint that a satisfactory theory of light should do justice to both that particle-like and the more familiar wave-like kind of behavior. Okay? And so despite Einstein calling this paper very revolutionary, he is not some sort of iconoclast that is just out there to tear down the theories of his contemporaries. Like, no, he is carefully probing nature, relying on this fixed point strategy, but sort of being prepared to let the chips fall where they may, even if it's as drastic as like compromising the wave theory of light. All right. Now the next question is like, why did this argument not convince anybody else? And so one obvious answer is that the wave theory was so well established at this point, that seemed to be one of the great advancements of the 19th century, that no argument would have shaken people's trust in that. But there is also another argument that we tend to forget, a century later, is that this argument was neither perfect nor new. So I already showed you it's not perfect, right? It only works in the Wien regime. The average energy of the light quanta is twice of what it should be. And then, of course, unbeknownst to anybody at the time, it really works for waves as well as particles. But it's also not new. So Wien had actually originally derived his Wien law on the basis of a shaky analogy between black body radiation and an ideal gas. And remember what Einstein wrote in 1617. He says, well, this these things are so similar, right, that can't be a coincidence. But my guess is that most other physicists did think it was just a coincidence, right? So they did not take it all that seriously. All right. So Einstein goes on, and so now, like in 1906, he is going to from the Wien law to the Planck law, which he ignores for the most part in the 1905 paper. And he famously writes, he's like, initially he thought that Planck was doing something different from what he was doing, but he's now realizing that Planck implicitly relies on the same assumption that he is making, namely the light quantum hypothesis. Now he overstates his case because, like, it's really not the light quantum hypothesis, it's the assumption that these resonators that are interacting with the black body radiation, that those are quantized. Okay? And so again, Ted and I, like, I think you got interested in like history of physics, like through this beautiful book by Kuhn on like black body radiation, right? And so Planck, there's now great consensus among historians, did not quantize much of anything. This relation equals NH nu does not mean that the energy can only take on values H nu, 1 H nu, 2 H nu. No, he is binning. This is the term I got from Ted. He's binning the energy, right? So E equals NH nu now means that if you're counting states, you should count everything between NH nu and N plus 1 H nu as the same state. And it takes until 1906 that Einstein points out, since this formula, goes for very high frequencies, that for high frequencies, it makes such a big difference whether it's H nu or N plus 1 H nu, right, that you can, and you believe in classical theory, that you can't possibly treat that as the same state. If you believe in classical theory, then you're badly undercounting like how many microstates you have. So the only thing that works is if you really quantize the resonator energy. And again, that is Einstein in 1906 and not Planck in 1900. So if you don't quantize, right, then you get the equilibrium, the equipartition value. And now, if you quantize, you have to do it something differently. So of course, the delta function is not in Einstein's toolkit, so he has a more clumsy way of doing this, but it amounts to the same thing. So now you're going to calculate the average energy, right? So now, like, it's a little different here with that here. So I'll go through this fast. So you introduce, like, beta is 1 over kt, and the partition function. You can write this sum now. It's just a geometric series. It's very easy to calculate this. And you find that this energy is given by that. This then is what Planck calls, or what I've earlier called, like the energy density of the resonator, right? That is equal to this. And Planck had put a lot of sweat and tears into finding the relation between the energy density in the resonator, the energy density in the radiation, and boom, you now get the Planck law. Okay? So this is the derivation that you often now find, like in textbooks. It's not the derivation of Planck, it's a derivation by Einstein in 1906. And Einstein immediately realizes that you can use these quantized resonators also to deal with another problem, namely the specific heats problem, right? And so there's like a famous comment by Maxwell saying, look, if you look at spectroscopy, it's clear that molecules have a lot of degrees of freedom, right? Just look at the spectra. And a lot of these degrees of freedom do not seem to contribute to the specific heat like they should, right? And he says, I have now put before you what I consider to be the greatest difficulty yet encountered by the molecular theory of heat. And Einstein has this very simple model to deal with this problem. Right? So he is considering like a lattice of just n of these molecules, all at the same frequency, knowing full well, of course, it's like a very oversimplification, but look what you get, right? So if you have the equipartition, you get like, the Dulong-Petit law. If you have this quantized energy, then you get this much more complicated expression, right? So now you have this, and if you now like look at this, you see that it's like the equipartition value, Dulong-Petit, times this formula, right? And so if x goes to infinity for very high temperature, this goes to 1, right? So then you have the Dulong-Petit law. If it goes to 0 for this is of course a mistake, for very low temperature, then you have like it's amazing how I've looked at this a million times. You only look at when you're presenting it. Then it goes to 0, right? And so this then very nicely explains this. This is like a graph that Einstein actually took from his own teacher, Weber, who was his only claim to fame was that he's done these experiments using snow as his coolant. So this explains then, why the specific heat of solids goes to zero as the temperature goes to zero, and why, answering Maxwell's question, like why a lot of these degrees of freedom do not contribute to the specific heats, because even the frequencies are so high that even at room temperature, they're like frozen out. Okay. Now, it turns out that the quantization of matter is more palatable than the quantization of radiation. In particular, like Walter Nance picked this up. Now, cryogenics has advanced tremendously. He gets some money to put up the first Solvay conference. Note that there's like a graph of the specific heats, like in the back here, right? Einstein talks about specific heats at this conference, but he continues to be more interested in the question about radiation. So a quick, what is Einstein doing? 10 minutes, oh Jesus. So he has meanwhile got his PhD. He submits, you have to do a second PhD, right, in Germany to advance. And sadly, the only thing that survives of this dissertation is the title. Consequences for the constitution of radiation of the energy distribution law of black body radiation. Okay, so he now teaches for a bit, then becomes like a professor at the University of Zurich, and he returns in 1909 to this Habilitationsschrift. And so I'm going to skip over all the details here, but the strategy is important here, right? So he says, we will try to proceed in the opposite direction than that taken by Mr. Planck. We consider Planck's radiation as correct and ask ourselves whether some conclusion about the constitution of radiation can be inferred from it, right? And I'm not the first one to notice that this is the strategy. Martin Klein, sort of my other intellectual grandfather, made this point a long time ago in the 60s. So Einstein is now going to do this, and instead of using the canonical ensemble, he's going to have his own derivation using Boltzmann's principle of this fluctuation formula. And again, I'm going to do what it's supposed to do, namely click through this, because I don't have time. The good thing is that all this will be posted, so you can look at it at your leisure. But boom, at the end, he finds that you get the same formula that you got from the canonical ensemble using nothing but Boltzmann's principle, S equals K log W. All right, and now he's applying against this to black body radiation. So, so in this case, the energy is the energy density times the volume and delta nu. This is black body radiation in a very narrow frequency range and a small volume. So you put this in, you get the derivation, the derivative with respect to T of this radiation density. If you do this for Rayleigh genes, you find this. That points to waves, just proportional to mean energy squared. If you do it for the Wien law, you get this. That points to particles. And if you do it for Planck, you get a sum of two terms. Okay? This is Einstein's famous result. And so he concludes, he says, the next phase of the development of theoretical physics will bring us a theory of light that can be interpreted as a kind of fusion of the wave and emission theories. Okay? Now, what does such a theory look like? Again, I'm interested in the strategy here, right? So initially he thinks, okay, it's going to be some nonlinear generalization of Maxwell's equation. He starts corresponding with Lorentz. Lorentz says that's a non-starter. And in Salzburg, when he lectures about this in September, he says it's much more deflating. He says the fluctuation formulas, he does it both for energy and momentum, offer few formal clues on which to build the theory. Imagine that the diffraction and interference formula are not yet known, but that you would have this fluctuation formula for the Rayleigh genes law. Who would have sufficient imagination to construct a wave theory on such a basis? All right. So again, result convinced nobody. Epstein was there, remembers, like, no, Planck immediately said, like, it was not necessary, too advanced. You know, Einstein is otherwise engaged for a few years, working on a little thing called general relativity. And when he comes back, you know, like there's the scenery has changed dramatically. Now you have the Bohr model. Einstein is very impressed by this. Again, like, you know, like I'm going to skip over these quotes. He returns to it in August 16 and finds like what he thinks is a beautiful derivation of the Planck law for like a very abstract Bohr atom. And what I mean by abstract is that Einstein never fell for the idea that you should picture like an atom as sort of a miniature solar system, right? The math, of course, is very convenient, but Einstein had this more abstract picture, it's just energy levels, right? And so in a way, like much closer to sort of the modern way of thinking about this, right? So here, you know, like you have the, you know, the famous three processes. Again, like this is a derivation that you all have seen before, so it's just a matter of like how quickly I can click through this. Yeah, no, the thing is, I want to get to. I was worried about this, but I want to get to like one last thing that I haven't talked about before, and so Einstein does a second derivation here where he looks at momentum fluctuations, and again, you know, like finds like, you know, the Planck law, right? So there's two derivations of the Planck law in this paper. But I don't want to, again, I want to use what little time I have left to deal with, again, convinces nobody to deal with like this bit. Quantum theory is a monatomic gas. So this is the last big step of Einstein before quantum mechanics arrives, and he takes his inspiration from Bose and de Broglie. And so, you know, like, this is like what he gets from Bose, like, you know, like the number of states in some energy shell, like E plus delta nu, right? So this is the number of states. And so it's this here. So of course the dq to the third, that's just V. It's the momentum part that matters. And you write it like this. And then it's just a matter of like once you have the P as a function of E, you can figure this out. Right? So this is the important part. And for photons, you have to multiply it by 2 to account for polarizations. You use that P is now E over C or H nu over C. You put this in, and you get this here. Right? So now this is going to give you the numerical factor of the Planck law, which Einstein, even in 1916, 17, had not gotten. This is what impressed him about Bose. And for Einstein is now going to do this for non-relativistic gas, right? So now E is just P squared over twice the mass. You get this formula here. And you know, you're now going to do statistical mechanics. You get like, you know, your Boltzmann statistics. And then Bose is doing this, right? Mimicking what Planck was doing in 1900 without, as he admits later, without having any awareness that, you know, what he's doing is anything funny, right? So now, of course, we know, like, well, this is when these particles are indistinguishable, then you do this, right? So you can find this. And the reason I talked about this problem with like n factorial at the beginning is that there is a dilemma, and the dilemma is very important for Einstein. So because like these formulas, they need to do two things. You need to have an entropy that goes to 0 if T goes to 0, and you need an entropy that is additive. Okay, and so like these calculations that I'm showing you here is to show that in the Boltzmann case, you're stuck with that dilemma. Okay, so in both cases you can get that the entropy goes to 0 for T goes to 0. The problem is that if you do the Maxwell distribution, right? Again, the fairly standard stuff, right? You know, like finding the equilibrium, Lagrange multipliers, and what have you. You get this equilibrium state, and you can see here because of that, right? This is not additive. Okay, so now you have a real dilemma. So with this n factorial, it's not additive. Without it, it doesn't vanish for t equals 0. Okay, you get this nonsensical value of this here. Now, for Bose-Einstein, it's different. Where for Bose-Einstein, it turns out that you do the same thing, and you now get like again, like, of course, this has to apply to like quanta. You now get the actual Planck law out. But you now find, if you do this, you find that the entropy is now additive. It meets both these constraints. And so why is then Einstein? So this, again, I'm interested in the Einstein's MO. Why is he taking the steps he's doing, right? So he's not saying, oh yeah, Bose was right. These are indistinguishable particles. That's why we should do this. No, Bose is completely confused about this. Einstein is not convinced that this makes any sense. But what he says is that, look, if it's only if we move from Boltzmann to Bose that we get an entropy that meets these two requirements, namely going to 0 for t goes to 0 and being additive. Right, so this is what he says. For these reasons, I believe that Bose's calculational method must be considered preferable, even if there are no a priori reasons for the adoption of this method with respect to others. Okay, so I think that's interesting. Now, why de Broglie? So here, what Einstein is doing. So this is why, I flashed up all this stuff about the fluctuation argument in 1909. What Einstein is doing is he repeats exactly the same calculation that he did for black body radiation, but now for this quantum theory of the ideal gas. What's that?
Are you saying that Einstein didn't invoke identicalness of the particles?
Correct. That's correct. So he says, so why, a priori, there is no reason to prefer this odd way of counting over Boltzmann, but the fact that it gives you these desired thermodynamical properties leads me to prefer this. And now he goes on to say, okay, so now, I'll maybe rather than continue this, I should answer your question. So what he's going to show, let me just click through. So he's going to repeat. I'll get to your question in a moment, right? So he's going to repeat the same calculation that he did in 1909, right? And the result is just going to be exactly the same. It's going to be a particle term and a wave term, and it's exactly what you got before. Okay, and so now Einstein writes it like this. Right? So now so he says right. So you have two terms, one pointing to particles, one pointing to waves, and then he makes this intriguing comment. He says how a material particle or a system of material particles can be assigned a scalar field of waves has been demonstrated by Mr. de Broglie in a very noteworthy paper, right? And so now, so to answer your question, my impression is that Einstein is now saying, look, it's not because of, it's not where you start with Bose, okay, it's identical particles, but in order to make sense of these statistics, right, you do better thinking in terms of waves and quanta of waves than in terms of particles. And that's why we should go with de Broglie. And this then is how he, one more slide. This is then how he paves the way for Schrödinger, right? So Schrödinger later says wave mechanics was born in statistics. All right. So what are the take-home lessons in terms of methodology? Don't just speculate. Extract as much information as you can of what you know. Once you find something that works, keep using it. Einstein is using this system of fluctuations the whole time. Be wary of coincidences. Keep your eye on the big picture. Don't let the perfect be the enemy of the good. Be prepared to let the chips fall where they may. Keep it simple. And then, before I start sounding like, a Dear Abby, advice column, I'd better wrap it up. So that's my story. Thank you.
Okay, questions? Yeah.
So if I understand right, it's that what today seems to us just obvious that, of course, there's such a thing as completely identical particles. Do you think the point is that Einstein just couldn't wrap his head or didn't conceive that a particle, like a molecule, could be intrinsically, like, fundamentally indistinguishable, but when he thought of it as a wave, that was a palatable
Yeah, I mean,
concept?
so again, what my impression is that, so, you can think of like identical, like, you have identical like pennies or something, right?
Yeah.
But still, you can, if you switch the two pennies, right, you would still say, but when it's money in the bank, right, there is no way to distinguish like, $1 from another dollar, right? And so that latter thing is more like when you think about these particles, the excitation of waves, that starts to make more sense. And so this is what also like, convinced Schrodinger, like, like if this is the statistics then we should move away from this idea that we have particles and we should move to these idea of waves. And so the other thing that I find fascinating, right, and came like, when we were discussing about it, is like how long it takes for the community to pick up on like, well, there's really something important about this aspect that once you think about these waves excitations, that you lose the property that these particles are localized. They're not like, point particles, like at a particular point. No, they live throughout this space. And so these ideas that now may seem like fairly obvious to us, like, it took time even for somebody like Einstein to, as you say, wrap his head around it. But what I find fascinating is that the way he does this is not to, oh, maybe it's this, but to really, and so, I mean, that's what impressed me about that talk you gave, like, like 20 years ago. Like, all right, this is what we know, okay? How does that box us in? And so we can take the next step without just like, trying to speculate. All right?
All right, other questions?
And I apologize for like, I talk really fast, but not that fast. Not fast enough.
Okay, well, let's thank Michel again.